Well, computer architects came up with something fun here and came up with this notion of paging. So instead of having variable size programs and have variable size segments or data segments, instead what you can do is you can take all of your memory and you can chunk it up into different fixed size regions. So for lack of anything better, let's say you have all of memory and you chunk it up into 4 kilobyte regions. And we call it a page. So what does this really turn into? Well, let's say we have the address space of a user here. And it thinks memory goes 0, 1, 2, 3. Over here, we have physical memory. And what you can end up with is a table which will map these different addresses into different locations, possibly out of order over there. And it's a chunk at a time. So if you go to access, let's say, address 0 to 4 kilobytes minus 1, you are accessing here. If you go to access 4 kilobytes to 8 kilobytes minus 1, you're accessing here. But this is a virtual address space. Once we go through the translation, if we go to access, let's say, address 4,182, we're actually going to get mapped up over here into physical memory. And just to introduce some nomenclature here, if you take a processor-generated address or a virtual address, if we go to look at what is actually inside there, there's a page number, which is this number here, which is which page to go look at. And then there's an offset, which is the low-order bits of the address. And the offset says where inside of this physical page to go find the exact byte we're looking for. And it's pretty common for these page sizes to be in the sort of few kilobytes sort of range. If you go look at something, I don't know, we'll take x86 for example. x86 default page size is 4 kilobytes, but it also has a 2 megabyte option and like a 1 gigabyte option. Some architectures like MIPS actually has quite a few page size options. So I think you can go anywhere from 4 kilobytes by maybe powers of 2 all the way up to, I think, maybe 4 megabytes. So you can have different page sizes. But for right now, let's just abstract that and just say there's a fixed size of some small number of kilobytes. Actually, the first original machines actually had these even be smaller. They had them be maybe about 512 bytes. But as memory got bigger, page sizes could get bigger. We'll talk about why you might want to have bigger page sizes. But really what happens here, this page table allows us to take a contiguous memory, a set of memory addresses, and map them into a non-contiguous space. Now, this can really get away from having fragmentation. Because all of a sudden, the worst we can be, the most amount of memory we can be wasting is a size of a page. So let's say you have 1 byte on this page here, and we call that as used. Well, your worst thing you're using is 4 kilobytes here, if it's a 4 kilobyte page. And this page, some other process can use. Because we have a very flexible remapping system. It's a complete mathematical map. So that's looking at if you have one program. We can extend this pretty easily to having multiple programs at the same time, where each program has a different page table. So if you have a processor, which is executing multiple programs, and let's say it's time multiplexing these programs, in physical memory, you can actually intermingle all the different pages of the different programs and do memory allocation where you try to pack the memory as tight as possible or reuse the memory as much as possible. And these really flexible page tables here will allow the remapping to be arbitrary. So you don't have these at least you don't have an external fragmentation problem. You may still have what's called internal fragmentation, where you're just not using the pages very effectively. So this is interesting up here. This figure here, we have OS pages. So what are OS pages? Well, the OS itself needs its own code and its own data. And many times in a paging system, the OS itself may not use a page table to go access memory, because it needs to go, let's say, start up another program, so it needs to be able to touch these bytes here and go kill a program or load some data from a particular application. So many times the OS is, to a large extent, held to a higher standard here. And the OS can actually go and touch all physical memory and not have to go through a mapping layer. OK, so here we have private address spaces per user. So something we have not addressed yet is, where do we store this stuff? And how big are these page tables? Well, they can get pretty big. If you want to basically have a program that can address 4 GB of RAM, you're going to need a page for each 4 kilobytes of those 4 GB. That's a lot of pages. So you need to store this somewhere. So the naive approach is you just have specialized register files in your processor that hold the entire page table. Unfortunately, that ends up being, well, for a 4 GB space with 4 kilobyte pages, ends up being something like, with I think a 32-bit page table entry, we end up something with like 4 megabytes. And if we have 100 processes running, that's 400 megabytes that we have to store somewhere. Well, that means we probably don't want to keep it in registers or register files in our main processor. Now, conveniently, as we have more and more RAM, this allows us to have more and more processes to run. It allows us to use more memory because we have more RAM in our machine. But also, we have more places to store page tables if we want to put them in RAM. OK, so maybe we want to put our page tables in RAM because as RAM goes bigger, we might need more page tables, but we have some place to go put it. And it's always the case that, well, if we design this correctly, if our page table entries are designed correctly, that the size of a page table to represent a certain amount of RAM is going to be less than the amount of RAM that you have to store in. So it's some fixed overhead. So let's take, for example, a page table entry which takes 4 bytes to represent 4 kilobytes of memory. That's 1,000-to-1 compression. So as you get more RAM, you're guaranteed to always have some place to put it because your RAM size will grow 1,000x faster than your page size. OK, challenges of storing this in RAM. If we want to go access a page, when we go to access a page here, we have to index this table. So every load we do before was just a single load. But now we're going to have to do a load to go read the page table and a load from the actual physical memory location. Well, we just doubled our number of memory references that we have. And that's kind of a bummer. So what do we do about this? Well, before we talk about that, let's talk about where to store the page table and the size. And then we'll talk about some techniques to speed up the access. So here, let's take a look at where to store a page table. If we have our linear page tables of what we've been talking about to this point, you can actually just go store them in RAM, and they'll map down to different points down here. And this works decently well. Unfortunately, these still have to be contiguous themselves. So we might get fragmentation problems in the page tables themselves, or different page tables fighting with each other for memory. They're hard to move. So we would like to think about some way to go solve this. We'll hold off for a second on how to solve that. But this is something to think about. It's kind of unpleasant here to think that your page tables themselves cause fragmentation. So I just wanted to sort of recap and show the mechanics of this, of what's in our page table. So in our page table, what we're going to store is we're going to have, well, first of all, we're going to have instead of having a base and bound register, like we had in the base and bound architectures, we're going to have a base that points to the base of the virtual, points to the base of the page table. And then we're going to have some structure in RAM, or structure in the page table here. And what does a structure look like? Well, there's probably a valid bit. There's a physical page number, which points to some place over here. And maybe there's some status bits also. We'll talk about those more in a minute, but you probably want some status registers there. You can track some information like how often a page is being used, which pages are used, maybe some statistics. Maybe you want to know whether you can read the page or write the page. Now, this last note here is sort of the key to time multiplexing a processor between different processes. As different programs execute, and you time slice or preemptively multitask between different operating systems, or just different applications on one operating system, what you're going to do is you're actually going to change this base register to something else. And effectively what this does is this completely changes your entire map of memory as you're executing. And this is pretty fancy if you think about it. You can just one write to one register, and all of a sudden all of memory looks different. And the protection is totally different for the application. Now you might be thinking to yourself, if I'm running in the operating system and I change this register, all of a sudden it changes the entire map of memory. How do I not crash the operating system instantaneously? Because all of a sudden the operating system's code just got remapped to some other location. Well, there's some magic behind the scenes here. This is what I was saying, is that there's a couple different approaches to this. The basic approach is the operating system will not use paged memory for its own purposes. It just uses physical memory for everything. And there's some special bit that says you're in operating system mode, and what you're doing basically doesn't have to abide by the paging system. That's one approach. Another approach is you'll have entries in the page table here that are all the same in every process, and it always maps the operating system in at a certain location. So you can change this willy-nilly, but all the things you go to change it to will have the operating system mapped to the exact same location. That's another approach that people use. And there's some things kind of in between those. Just to flip back here, one thing I did want to point out is it's important that an application is not able to modify its own page table or modify other applications' page tables. And hence, this application here tries to go access something. It looks up in the page table, and it says, oh, that's down there. It's important that this does not overlap with someone else's page table. All of a sudden, you'd allow an application to be able to change its own memory mapping. And that would be quite dangerous. OK, so far we've talked about, actually, before we move off this, let's talk about the exact mechanics of this. So you have a virtual address. It has this virtual page number and an offset. This is actually an index into this table. It's just a basic index. It's one huge table. And it just indexes into here, and it gets some bits. and those bits get basically replaced, to take a virtual address into a physical address, we're going to take the virtual address and we're going to take the virtual page number, and we're going to remove that. We're going to use that to index into here, and then what comes out of here is going to be used to be the new high order bits of this address, and we're going to call that the physical address. One last note about this. We talk about here a disk page number. We're going to be talking about this more at the end of today's lecture. But it's possible that you might want to use this location here to say the bits for that page are not here right now. They may be on disk. We're going to talk about more advanced. This is the virtual memory subsystem. But a lot of times, a convenient place to locate that information is in the page table itself. OK, so let's crank through some math very quickly here. This page table is relatively large. So let's take an example here, a 32-bit address space. It has 4 kilobyte pages, and each page table entry, PTE, is 4 bytes. So there's 2 to the 20 page table entries. Each of those is 4 bytes big. This is a megabyte times 4. We end up with 4 megabytes. OK. So that's 4 megabytes for this table per user process. And this assumes that we only have, let's say, 4 gigabytes worth of address spaces, or address space, 4 gigabyte address spaces. That's not too horrible. If you have 1,000 processes running, that is pretty bad. And if you go type top on your system and you go look to see how many processes are running, you probably have a few hundred running. So if we use this linear page table notion and you had 1,000 processes running, all of a sudden you'd be using 4 gigabytes of memory, which is your entire address space on a 32-bit machine, just for the page tables, and have no place to put actual data. So I'll give you guys a hint here that people typically don't use linear page tables because it's not very storage effective. Now, what are some approaches to make it more storage effective? You can go to larger pages. So instead of having 4 kilobyte pages, we have 1 megabyte pages. So that would take the number of page table entries and dramatically shrink it. And it would also dramatically shrink the linear page table size. Some downside is you start to have some more internal fragmentation. So if you use 1 byte onto a new page and the whole rest of the page is empty, you'll be wasting a megabyte minus 1 versus 4 kilobytes minus 1. So you have a higher amount of internal fragmentation. Another challenge is that on a page fault, you're going to have to pull in a lot more data. Instead of pulling off of disk, we'll say 4 kilobytes of memory, you might have to pull a megabyte. It's just bigger numbers to deal with, and this could be painful. So let's think about actually let's move from a old computer to a more modern computer. So a more modern computer, we have much larger address spaces. We want to access larger amounts of memory. So my laptop has 6 gigabytes of RAM. Well, 6 gigabytes of RAM, that's bigger than 2 to the 32. We can't address that in a 32-bit machine. And in fact, my laptop is a 64-bit machine. So let's crank through the math now for, instead of having a 32-bit machine, having a 64-bit machine. Well, if we have relatively large pages, let's go for a megabyte page. And well, a megabyte page is going to give us 2 to the 44 page table entries. And these page table entries themselves are probably bigger because the output of them has to be, let's say, 64 bits instead of 32 bits because the page address is larger now. Well, all of a sudden, one process page table is 35 terabytes. Well, my laptop is a 64-bit machine, but I don't have 35 terabytes of RAM in my computer. Won't physically fit in my laptop. It can't lift up 35 terabytes in today's technologies. Well, that's a bummer. So can we just not go to page systems with 64-bit address spaces or larger address spaces? Well, no, the world's not that unforgiving. We do have some saving grace here. We can think about going to different arrangements of our page tables. And the other nice thing is if we go to more space-dense arrangement of our page tables, or we can go to the notion that our page tables don't always have every single page being used. So for instance, in this linear page table here, I have some slash locations. And what this means is this is some location in memory which doesn't have anything mapped there. So if this is not mapped, why do we want to store or use the storage for that space? So we can actually go up with a sparse representation of our page tables that only have the portions of the page table that we actually need. And it's possible that if every single page in your page table is filled out, you may not be able to get away with a sparse representation, and you might need all 35 terabytes to map one process. That's just one process. If you have 1,000 processes, multiply this by 1,000. Well, the saving grace there is, by definition, if you're going to have one process which is going to map 2 to the 64 locations of memory, that means you have 2 to the 64 locations of memory probably in your address space somewhere, and that's a much larger number, or in your physical machine rather, that's a much larger number than 35 terabytes. So this compression of the page table entry always being smaller than the page itself allows you to always store the page table entry into the memory that you have, because it always grows to be able to fit inside of the amount of physical memory you have. So how do we go about doing this? Well, one representation that we can think about is having a hierarchical page table. So instead of having one big table that is linear, we have a table that we index into, which tells us where to go look for more data. And then we look in that table to look for even more data. So here we actually show a 2-level page table. And what's interesting is if we have an address here, we index into here, we can actually rule out huge portions of the address space very quickly by just leaving this particular entry in the higher levels of the page table empty. And then as we go drill down a little bit farther, we can also have empty entries. So with this, if you go look at our virtual address here, we're actually going to use different portions of the virtual address to index into other structures. And we can take this sparsity into account. Another cool trick we can do is we can actually reuse, if you have a hierarchical page table like this, you can actually reuse sort of middle-level page table entries between different processes if they're mapping the same space. So for instance, if they're mapping the same instructions, you can actually just reuse all these page table entries between two processes and have multiple pointers coming into here. One thing that this does not change is you still have one page table base pointer per process or per user. You don't need to have bases over here because the bases of the second level come out of the first level. So it's a tree. And here, this is just a 2-level, but there are plenty of architectures that have more than 2 levels of page tables. So if you go try to build a 2-level page table, which is relatively unsparse, on something like a 64-bit machine, it still becomes very large. So as you have more and more address space, your address space by definition has to be less sparse if you have a sort of fixed amount of memory in it. So what people will do is they'll actually go to maybe 3 levels or 4 levels of page tables. Now some downsides of this is we just took something that was we took a load, which took one memory reference, and we had to add an extra memory reference to go look up in our page table, which was in memory, to go find the actual address of the physical address. And all of a sudden, we turned it into 3 memory references, one to do the actual load, one to look in here, and one to look into here. So every level of page table that we add could potentially add another load. Ugh, that's not very pleasant. But before we get to that, and ways to fix that, let's look at how this gets laid out into memory. So before, we had all of the page tables sort of up here, and we had to deal with fragmentation between the different page tables. But now, because we have a multi-level page table, we can allocate it out of our physical memory addresses sort of in an ad hoc manner. And one of the cute little tricks that most operating systems do, and most systems do, is they make the size of one of these levels of tables to be the exact size to fit in a page. Because then you can locate it easily inside of a page. And you can allocate it like a normal userland page and just sort of mix and match it somewhere into the different locations and intermix it. So that's pretty convenient. This solves our external fragmentation problem for our page tables themselves. And we can use sparsity in our address space to use less space for our actual page table. So page table itself is smaller. Downside is we might have to do multiple memory references to be able to resolve a page table address.